Okay, so we are on the grade Google Classroom. Remember, this is probability stuff that we're looking at now. I see the exercise solutions are there as well, but yeah. So the note that we did is on here, and it starts with introduction to probability. And we were talking about impossible events and certain events. So the probability of an impossible event would be 0. The probability of a certain event would be 1. So that is why in D of that question, where they asked, what is the probability that you will arrive at school? All right, they didn't say, they just said you're either going to arrive late or you're going to arrive on time. So that means that you are definitely going to arrive, whether you're late or on time. All right, so that is why that probability was 1, because it's a certain event that you will arrive at school. Okay, we can look at that now again. Then we spoke about experiments, we spoke about relative frequency and experimental probability. Remember that? That was the first thing we actually did, was where they tell you like a coin was flipped 10 times and 7 of the 10 times it landed on heads, right? So then the relative frequency of landing on heads would be 7/10. So if they're giving you specific values based on a specific experiment, then you use those values, okay? So relative frequency is stuff that actually did happen, and they're telling you what happened. Then when we do probability, so I think we did also do exercise 1, that should be in the books. Then when we did theoretical probability or just probability, that is before you even doing an experiment. What do you think will happen? So now if I ask you, what is the probability of a coin landing on heads? What is that? Heads is one of the sides of the coin. How many sides are there? 2. All right, so 1/2. That's the probability. That's what we think would happen. So if I'm flipping a coin 10 times, how many times out of 10 do I think it will land on heads? What's a half of 10? 5. All right, but guys, that is just what we expect to happen. That won't always happen. Okay, so probability is what we expect will happen. Relative frequency is what happens in an experiment. Okay, so if they're giving you specific values, if they say, we flipped a coin 10 times, it landed on head 7 times, then you must kind of forget about the probability, what you thought would happen, because they're then telling you what happened. Okay, so then you use those values. You see, this is a big note. This whole thing, remember we went over what actually happens in a deck of cards. We still wrote that stuff down. It's important that you know that as well. And then exercise 2 we also did. Then tree diagrams. This was the last thing that we did. Okay, so just to revise what happens with tree diagrams, the possible things that can happen, you put on what we call branches. So when you're flipping a coin, it's either going to land on heads or tails. So you do a heads and a tails branch. All right. Then you also write the probabilities of each of those outcomes. So the probability that it will land on heads is a half. Probability that it will land on tails is also a half. All right, something that's important is that on one set of branches, whether it's 2 outcomes or maybe even more than 2, all the probabilities must add up to 1. Okay, we'll look at that now when we actually look at a tree diagram in number 2. So that's important. So if you have this probability plus that probability, they always have to add up to 1. So a half plus a half, that is 1, right? Then if you flip a coin twice, this first set of branches represents the first coin flip. The second sets of branches here represent the second coin flip. But we did them twice because we're actually trying to summarize all of the possible outcomes, everything that could happen. So your first coin can land, or the first time you flip the coin, it can land either on heads or tails. But now if the first coin landed on heads, the second one again will either land on heads or tails, right? And if your first coin landed on tails, the second one can again either land on heads or tails. That is why we do 2 sets of branches. Okay, then at the end, we need to list our final outcomes. So you have a possible outcome of getting 2 heads. And remember, we follow the branches leading up to that. So heads, heads. Or the first one can land on heads and the second one on tails. So that's the second possible outcome. Or the first one can land on tails, second one on heads. That's the third possible outcome. Or both of them can land on tails. Sorry, and in both flips, they can land on tails. Okay, so you always list your final outcomes like that. Then if they're asking for the probability of the coin landing on heads twice, on heads the first time and on heads the second time, you take the probabilities on your branches and you multiply them together. Right? Do we remember that? I know we did this a long time ago, but that's what you always do. Right? You always take those values, those probabilities, and you times them together. If it's more than one thing, so here they said, if you want to find the probability of getting one head and one tail in any order, you have to consider heads, tails, and tails, heads. Because if they say, I want one head and one tail, they're not saying first heads and then tails. They're saying one head and one tails. So it can be this outcome or that outcome. All right. And if it's multiple outcomes in your tree diagram, you have to find the probability of each of them and then add them together. Right? Does that ring a bell? Do you remember that? So that's why they're saying here the probability of one heads and one tails would be these two probabilities added together. Probabilities of heads, tails, and then tails, heads added together. And then to calculate each of them separately, you're going to say a half times a half. That's the first one, plus a half times a half. That's the second one. And then they just did that calculation. All right. This was this is an example that we did. This was the bar one example that we did. And here is the exercise. Okay, so question one, that's the one we just marked. So see, they gave us the tree diagram. Consider the tree diagram below and answer the questions that follow. Now guys, what I want you just to notice is that the probabilities on each set of branches add up to 1, all right? 0,7 plus 0,3 is 1. So guys, if they told you the probability of you remembering to put your alarm on is 0,7, what is the probability of you forgetting to put your alarm on? Then you need to know that it is 0,3. Because what must you add to 0,7 to get 1? 0,3. All right, these two must always add up to 1. So they often just give you one of the values and you must know what the other value is. Okay, we will do examples like that. Then if your alarm is on, the chances of you coming early is 0,9, but arriving late is 0,1. If your alarm is off, the chance of you getting to school early is 0,2 and getting to school late is 0,8. All right. Now they're saying, what is the probability that my alarm will be on and that I will be early to school? So we say alarm on and early. And what am I going to do with those values? I'm going to times them. 0,7 times 0,9. Okay, that was the first answer. Alarm on and early, 0,7 times 0,9. Okay, the two probabilities on the branches you times together. If you type that into the calculator, this comes up, this fraction. You can leave it like that, or if you press the SD button, then it will give you the decimal form. All right, it's up to you whether you want to leave it as a fraction or write it in decimals. It doesn't matter. Okay, next one. What is the probability that my alarm will be off and that I will be early to school? Now you're going to say alarm off times early. So we follow those branches, right? So alarm off is 0,3 times early is 0,2. 0,3 times 0,2. Again, the calculator gives you this answer, but if you press SD, it will give you that value. Okay, you can write either one, it's fine. Next question. Therefore, what is the probability that I will be early to school? Now, guys, there are two final outcomes here that have me coming early to school. Do we see that? Either my alarm is on and I arrive early, or my alarm is off and I arrive early. So we need those two probabilities, and then because it's multiple ones, I'm going to add them together. Does that make sense? It's like having the heads, tails, and the tails, heads. We find the two probabilities, we add them together. C is saying, what is the probability that I will be early to school? Now they're not saying alarm on or alarm off. All right, they're just saying early. So I have to take this probability, right, plus that probability. Now guys, this probability is what I calculated in A. Alarm off times early. This probability is what I calculated in B. Sorry, alarm on times early, that was A. Alarm off times early was B. So now I'm going to take my answer from A and I'm going to add my answer to B. All right, so there we go. Probability of coming early is probability of alarm on and early plus probability of alarm off and early. Okay, alarm on and early, do we see that was what we got there? That answer, right? 63 over 100, or you can use the decimal. Plus alarm off and early, that's what I have there. Right, so plus the fraction or that decimal, and you get the answer. 69 over 100 or 0.69. All right, that's the probability of you arriving early. Whether your alarm is on or off, it doesn't actually matter. They're not saying that in that question. Okay, then D was the last question. What is the probability that I will arrive at school? Now, guys, obviously in real life, sometimes you don't get to school. All right, you're sick, you don't get to school, whatever. But we need to go on what they've given us. All right, we're not going to think now, oh, when I am sick sometimes, then I'm not going to go to school. So the probability can't be 1. All right, we need to go on what they've given us. And are they saying anything here about not arriving at school at all? No, so we need to assume what's given here is that this person will definitely arrive at school. Okay, whether they're early or late, they're going to get there eventually. So that is why that probability is 1. Okay, yes. Then you must say 100%. Okay, but you can't just say 100, but 100% is fine. Yeah. Okay, guys, number 2, just quickly talk about this. A bag contains 7 balls, 3 are black and 4 are yellow. 1 ball is taken from the bag and its color is noted. Then the ball is put back into the bag. Another ball is taken from the bag and its color is noted. All right, so we have 7 balls altogether, 3 black, 4 yellow. We take a ball out, we check what color it is, and we put it back. So we again have 3 black balls, 4 yellow balls, so 7 altogether. Then we take out a second ball. All right, so this is what your tree diagram is going to look like. Copy that down if you don't have it, please. So when you draw the first ball, when you take the first ball out of the bag, you're either going to take a black ball or a yellow ball out. All right, there were 3 black balls, 7 balls in total. That's why that probability is 3 over 7. There were 4 yellow balls, 7 in total. That's why that probability is 4 over 7. Guys, what's 3 over 7 plus 4 over 7? What's 3 plus 4? 7. So that's 7 over 7. And isn't that the same as 1? Okay, good. Then we're taking the ball out, then we're putting it back into the bag. So when we draw our second ball, we still have 3 black balls, 7 balls in total. 4 yellow balls, 7 balls in total. All right, we do our second set here at the bottom. All right, coming off of if our first ball was yellow. We also need to say the second one is either going to be black or yellow. Still 3 over 7, still 4 over 7. Then you need to list your final outcomes. I'm going to talk about this pink just now. All right, I'll explain now where that comes from. So now they say go tree diagram. Okay, we did that. In B, what is the probability that both balls are black? Okay, so now we're going to go first ball black and second ball black. All right, so we times those probabilities together. So black in the first draw multiplied by black in the second draw, we get 9 over 49. Okay, C was what is the probability that both balls are yellow? So we're going to do yellow times yellow. All right, 4 over 7 times 4 over 7, we get 16 over 49. Then the next one was, what is the probability that the first ball was black and the second ball was yellow? So now we need to follow those exact branches, all right? So black for the first ball, 3 over 7, times yellow for the second ball, 4 over 7. And we get 12 over 49. Guys, none of these fractions can simplify, but if they could, you would have to, all right? So I suggest type the sum into the product, I suppose, into your calculator, because the calculator gives you the simplified fraction always. Okay. E, what is the probability of, this is the same type of question as up at the top, that you had a black and a yellow ball in any order. So it could be first black and then yellow, or it could be first yellow and then black. All right, they just wanted 2 different colors. So we have to find the probability of black, yellow, which we found in the previous question already, right? 12 over 49. Then we add the probability of yellow, black, which is 4 over 7 times 3 over 7. Then we get our answer, 24 over 49. Then the last question was interesting. They said, what is the probability of getting at least 1 yellow ball? All right, now guys, that's what I circled here, the pink ones. All right, when we have 2 black balls, do I have at least 1 yellow one? No, there are no yellow balls. All right, so I'm not going to take that one. If I have black and yellow, is there at least 1 yellow? Yes, so that one we need. All right, if I have yellow, black, is there at least 1 yellow? Yes, so that one we need. And guys, by the way, we already calculated the sum in E, right? 24 over 49. We already have the sum of these two. It was 24 over 49. If I have 2 yellow balls, is there at least 1 yellow ball? Yes, so I must take this sum that I got in E and add the probability of 2 yellow balls. Now, have we maybe calculated that before? 2 yellow balls was 16 over 49. So do you see why I just added those 2 fractions together? We actually already calculated them. Guys, if you didn't notice that, it's fine if you did the multiplications again and added them. All right, you're not going to lose marks. So if you see, okay, it must be blue, yellow, oh, sorry, black, yellow, I'm going to do that times that. Plus yellow, black, I'm going to do that times that. Plus yellow, yellow, I'm going to do that times that. You're going to get all the marks, you're going to get the same answer. Okay, 40 over 49, that's the final answer. Okay, how do we feel about tree diagrams? Okay, because that's something that you need to know for the test. Now I want you to quickly copy down this note. A two-way table. There we go. So just make a little heading and just say probability two-way table, because obviously this one I'll be after the starting this note. Two-way tables is a table that shows the outcomes of 2 different experiments. All right, so far we've done 1 experiment. Okay, we flipped a coin. But then if we did flipping a coin and rolling a die, we could have used a tree diagram to show that, or we can use the two-way table. Okay, so just copy that down and then I'll run through the explanation. Going there. Okay, two-way table. I don't know if you kind of already figured it out while you were copying it down. But there we have 2 things happening, right? So 2 experiments. So you are flipping a coin and you're rolling a die, all right? It also would have counted as 2 experiments if you flipped a coin twice. Because then the first flip is 1 experiment, the second flip is another experiment, okay? So what you do is you put the possible outcomes of 1 of the experiments at the top. It doesn't actually matter which one goes at the top. You could have done it the other way around. So you put the possible outcomes, so what could possibly happen in the 1 experiment at the top of your table, and then what could happen in the other experiment going down your table. All right, so what I did here was, do we agree that when you are rolling a die, it's going to land either on 1, 2, 3, 4, 5, or 6? What if they tell you that it's an 8-sided die? They can do that as well. Okay, then what would it be? 1, 2, 8. Okay, so that's the outcomes, or those are the outcomes of the one experiment of rolling the die. Flipping the coin, the possible outcomes are heads or tails. Now guys, you could have done it the other way around. You could have put heads and tails at the top, and then you could have done 1 to 6 all the way down. Okay, that also would have been fine. It doesn't matter how you set up your table. So I'm saying you could have done this, H, T, and then 1, 2, 3, 4, 5, 6, going down like that. Okay, that also would have worked. It just would have been long, but that's fine. Long going down. Okay, then what you're going to do in the actual table is you're going to match them up. So what I did here is this is saying if you're rolling your die, it can land on 1 and the coin can land on heads. So that will be heads and 1. Right? Does that make sense? Or it can land on tails and 1. So that's what you're writing in the actual table. Then it can land on heads and 2. So heads and 2. Or tails and 2. So tails and 2. Right? Do you see? So you almost match up the headings in the actual block. So here your coin can land on heads and your die on 3. So that's heads and 3. Or coin on tails and die on 3. So that's tails 3. Right? Do you see? So you match all of them up. H4, H4. T4, T4. H5, H5. T5, T5. Right? Heads and 6. There we have heads and 6. Tails and 6. There we have tails and 6. Right? So you're matching them up. What you are putting in these blocks is similar to what you would write at the end of your tree diagram. So if we're thinking if we drew this as a tree diagram, we would have done heads, tails. Right? Let me do it here on the back. Heads, tails. Then how many possible outcomes are there when you're rolling a die? 6. What a nightmare. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. One, 2, 3, 4, 5, 6. Then your final outcomes would be you matching them up. So heads and 1, H1. Heads and 2, H2. Heads and 3, H3, H4, H5, H6. And then also tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. How many possible outcomes do we have there all together to count all of them? 12. How many blocks do I have in my table? 12. All right. So instead of matching them up as branches, one leading onto another one, we're matching a row with a column. Right? Heads and 1, heads and 2, heads and 3. Right? Does that make sense? So it's just a different way of summarizing the possible outcomes that you can have. Okay. So here we have the possible outcomes of rolling the die. Here we have the possible outcomes of flipping the coin. How many outcomes are in this experiment? How many pairs? How many blocks do I have in my table? 12. Right? So you can count the blocks. Or you can do it like this, if you're just thinking of it. If you have like lots of blocks, you don't want to count all of them. You can take the number of outcomes for flipping the coin, which is 2, and then times it by the number of outcomes for rolling the die, which is 6. Right? So you can times those two together. It will give you the same answer, or you can just count the blocks. Okay? Now, guys, when you're now doing probability, it's going to be over 12 every time, because that is how many possible outcomes you have. How many possible combinations you have. So all your probabilities are going to be over 12. So now they're saying, what is the probability that the coin landed on heads while the die landed on 5? How many heads and 5s are there? Heads and 5 is only 1, hey? Out of how many possible outcomes? 12. So 1 over 12. Right? Do you see how you use the table? Sure. Next one. The coin landed on tails. What's the probability that the coin landed on tails? How many blocks are there with tails in those blocks? 6. Out of how many blocks in total? 12. So 6 over 12. And if you simplify that, that's a half. And guys, isn't that the probability of a coin landing on tails anyway? Is a half. All right, so it does work. Probability that the die landed on 1. How many blocks are there with a 1 in them? 2 out of 12 blocks in total. Right? So 2 over 12. Which simplifies to 1 over 6. And guys, isn't that the probability of a die landing on 1 anyway? 1 is one of the numbers out of 6 numbers in total. Okay. What is the probability that the coin landed on heads while the die landed on an odd number? So now we're looking for heads and an odd number. So that's heads and 1, heads and 3, and heads and 5. How many are those? 1, 2, 3. Out of 12. So 3 over 12, which is 1 over 4. Okay, does that make sense, guys? All right, let me just check. Yeah, our time is basically finished and we haven't marked the homework. I'm going to post the homework answers on Google Classroom, but we will go through them on Tuesday. Okay, so I see you guys again on Tuesday. We are starting similarity on Monday. So you need to check the Google Classroom page for that video. Yes, Nathan? What's it? Also, 50. Yeah. All right, so guys, please remind me to go over this homework on Tuesday. All right, I will post the answers now in a bit. So you can mark, but I just want to make sure that you all know what's going on. Yes.